Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media. 2022 was an eventful year for Dotphoton. The Zug, Switzerland-based company, known for its raw image compression solution, competed at Vision Startup World during Vision Stuttgart, and was named a finalist for a Prism Award in the software category for its Jetross solution. Dotphoton also inked a partnership with Hamamatsu Photonics to pair JetRaw image data compression with Hamamatsu's scientific imaging technology. JetRaw combines file size reduction ratio with high processing speed, and the partnership builds on a separate deal that Dotphoton struck in late 2021 with Teledyne Photometrics. Bruno Sanguinetti, Dotphoton's co-founder and head of R&D, is the mind behind much of this powerful technology, and he joined us from Switzerland to discuss Dotphoton and its place in the photonics and machine vision landscapes. In our interview, Sanguinetti explores the confluence of sophisticated technologies that power Dotphoton's image compression capabilities. The first thing to understand is that for all their utility, standard images, or raw images, are actually somewhat of a dormant resource. That's where Dotphoton comes in. When raw imagery is too large to transfer and store, and takes too long to process, valuable information remains out of the hands of users who need it most. As Dotphoton says, the company's technology unveils the power of raw images and boosts big image data for critical and professional applications. With a life sciences background of his own, Sanguinetti says these applications include microscopy and endoscopy, but they also extend into aerospace and defense, space imaging, and agriculture. There's also vast possibility in machine vision, and that's where our conversation begins. The reality here is that the distinct technologies that combine to constitute machine vision are progressing at different rates. That puts a company like Dotphoton in the sights of many, whose ambitions lie in the ability to leverage the best and newest advances in compute, software, and AI, as well as in imaging, scanning, and sensing. Perhaps it's no surprise that Dotphoton was busy in 2022. As we conclude our own year of All Things Photonics, here again is Jake Saltzman.
So machine vision in some ways brings together multiple distinct technologies. It's very much its own animal, but the rate at which these distinct technologies advance, image capture technology versus the rate at which image processing advances versus the rate at which AI and deep learning advance, they're not always in alignment. They develop at different clips. And you're someone who's versed in all three of those very relevant areas. To begin, can you classify the present state of machine vision industry, given that we have all these converging areas?
Many technologies have evolved very well in the past. So maybe in the last 10 years, sensors have become better and better, first of all. So the latest sensors are effectively perfect. So you measure every single photon, you have very close to zero noise. So that has come a really long way. On the other hand, in the processing, with Moore's law coming towards an end, but not yet, actually, the development of processing power, especially with GPUs, has evolved very significantly in the latest years. There are still things to do. And as well, on the networking and storage side, things have evolved, but at a much slower pace. So had storage, for example, grown at the same rate as it has since the 70s, then we would be paying 1 cent per terabyte or 10 cents per terabyte of storage and about maybe a couple of dollars per terabyte of RAM. So that hasn't materialized just yet. There is still some work being done in those perspectives, but that's also one of the reasons why we went for compression first. But it doesn't mean that the other aspects aren't of interest for us. They are. As well, one very important new development, which doesn't relate necessarily directly to machine vision, but we do see a big shift to the cloud. So whereas before, if you wanted to have access to vast amounts of computer power, you really needed to have some in-house experts to set all of that up. What you can do now is you can rent it in the cloud. And so this opens up some possibilities, and it also allows more companies, especially startups, to participate in and to deliver products which are actually quite complex in the medical field, in automotive, in other like more industrial machine vision. And so this is accelerating machine vision from our perspective very, very much. So, and the cost of the cameras has gone down a lot, very significantly. You can get some kind of cameras for $99, which you can work with. So there has been a lot of development. On the other hand, there's still a lot of work to do. So what I like to say is that whereas machine vision is a technical subject, but it still doesn't have the technical engineering methods that are applied in other disciplines. For example, if you go to the supermarket and buy a kilogram of potatoes, actually the way that kilogram is defined is standardized, and you buy it in one supermarket and you get exactly the same in the other supermarket, and that's completely well defined. If you plug your computer in a 110 volt or in a 220 volt outlet, the voltage is very well defined and you know that it will work. On the other hand, if you take an image from a camera, it's still a picture. You don't necessarily have the very tight specifications that you would require to know that that is going to be compatible with your algorithm. So the current state now, and where I do see a lot of work going on, is in standardizing what, on the metrological point of view, what is that image, to make it not to change it from just being a picture to being a proper measurement.
You mentioned you mentioned us. In this case, that's Dotphoton, and I do want to jump into the Dotphoton technology. For someone who's unfamiliar, it's a somewhat daunting technology to look at, right? It incorporates usable information that pertains to so many areas of not just vision, but photonics, right? We're considering quantum properties of light. It can be deployed for microscopy imaging. The data it considers is traceable metrologically. To describe the technology, it's sort of really to bounce around the field of photonics. If you could, for our listeners, can you just sort of outline in the broadest scope possible the Dotphoton solution?
So you're completely right that our technology looks at the kind of holistic view of what an image is, and the advantage is to have the traceability of how that image was captured and to carry that traceability through your processing pipeline. And often the first step in your processing pipeline can be compression. And it turns out that if you know exactly how the image was acquired, you can do that compression in a much better way. And not only that, but you can embed some extra information in the image, which will be very, very useful later on. So you can kind of standardize it. Historically, we do come from a company that used to make some quantum sensors. A company still exists. It's called ID Quantique, and me and another colleague come from there. Very high-end sensors, so really single photon detectors. And at some point, we saw that sensors are becoming perfect. So the market in that side is becoming very competitive on the sensor side. And so, but we had an understanding also coming from cryptography, from information theory, of how light carries information and also how detectors work. And we thought, well, let's put those two things together to, as well with some of the knowledge that we had acquired at the university, to build some software that we think will be the most useful in the coming years. And that vision kind of realized, we see that at the time, machine learning was not as big as it is now. So we started 4 years ago. And we had this vision that the whole of image processing had been developed over many decades, specifically for the human eye, and that still many algorithms had been developed for the human eye, and they're still in use today for machines. And making those algorithms work specifically well for machine vision could have some advantages. And also the other aspect is that in large companies, you often have many, many departments. So a department is responsible for the sensor, another department is responsible for the data storage, another department is responsible for the analysis. And you lose over that whole chain, you do lose some of the information that was available in the beginning. So our vision was, well, if we make that information available in the files and we make it easily accessible down the pipeline, then the person who's doing the machine learning at the end of the pipeline, he can take full advantage of the knowledge of people coming before, and he can make really the most of it. And that is something which was possible for a small company because we were just not many people, so we talked to each other every day.
Dotphoton is very much filling needs in the sectors that deploy its technology. In diagnostics and medical imaging, which are the fields around which the company has finalized two of its most high-profile partnership agreements, the need to optimize the quality and amount of information that a user is able to obtain from an image stems from the fact that the sheer amount of data that is available is growing steadily every year, and that's just in diagnostics. This naturally places a heightened focus on automation and AI, and specifically the role it can play in ultra-quick data processing. Still, as it relates to the data acquisition process, even highly advanced algorithms can have a tough time working with image data in multiple formats. For example, after it has been compressed or processed. With a primary focus on efficiency and avoiding duplication, Dotphoton stresses the importance of practical interfaces.
I think the range of partnerships and the nature of the partnerships that Dotphoton has formed speak to the durability of the Jetross solution and the company's technology as a whole. I want to talk about biomedical and biomedical imaging here for just a moment. Many of our listeners are likely familiar with the topics of AI for surgical robotics or pharma inspection, machine safety, fairly well-documented applications. But each of these topics sort of veers into what we might consider health or wellness. And that's certainly been a major sticking point for your work to date. The combination of machine vision or machine learning and health is kind of dynamic. So can you explain for our listeners some of the work that's being done in this area, machine health?
Yes. So now cameras are being inserted into microscopes and diagnostic systems more and more. And the data in that field is growing very, very much. Typically, we see with our customers that it grows at a rate of 50% every year. And in a few years, it's going to be in the exabyte scale for everyone. So what they're doing some very, very interesting work, especially in diagnostics. So whereas if you have some illness, typically before you have an operation, you need to have a diagnosis which is based on some evidence, which is a tissue sample. And that process does require some time if it's humans analyzing it. And there's a lot of work that's being done in order to automate that. And so you acquire the sample, instead of looking at it with your own eyes through the microscope, which actually is still very, very common, you would acquire it with your microscope, and then you would analyze it automatically, and you would highlight the areas which the machine learning system think are most important, and then the doctor would check that the diagnosis is correct. But automation in that respect is very important in order to have the diagnosis quickly. So that's what area that we're working on. In particular, where is that now is that there are algorithms that work really well. On the other hand, they depend very much on the acquisition chain, meaning that if you have a specific hospital that has a specific way of collecting the data, of acquiring that data, of compressing it, of processing it and putting it into machine learning, the machine learning is going to work reliably in that context. However, if you then want to reuse that same concept in another hospital, then it will probably not work quite so well. And so unless you retake the whole chain. So what we're working on is on putting some very well-defined interfaces saying, well, at this point, you need an image which has exactly these properties for that machine learning to work reliably. And that is still very undefined. So that's where a lot of the work that the community is doing is aimed at. And yeah, we try to contribute our part there.
Just staying in the biomedical space for a moment, biomedicine moves fairly quickly as a technological industry. What message do you have for the instrument developers, the microscope developers about this technology? Because in some ways you're on the same page about what you want. In other ways, what you're doing is fairly new, and your solution is not just tailored for biomedicine, it's industry agnostic. What message do you have tailored just for the instrument developers in biomedicine?
So what we see is that often the way the images are developed in biomedicine are to look good to the end user, to their eyes. And that, of course, it's great. They, at the end of the day, they are responsible for the diagnostic, so they need to have images that look good to them. But they do fix a lot of the processing in that image. And they do use compression, which is quite lossy. So the message is, at least with our technology, we managed to have way higher compression ratios than what is achieved even with, say, JPEG. And what we also have is a full quality and the ability, so the images are still raw, so you can develop it for the screen of the doctor, the pathologist, and you can also develop the same image in optimizing it for a machine vision system. So the message is that you can now do many things with no compromise, whereas before you had to compromise speed of the system with respect to image quality or how it looks to the end user with respect to how good it is for machine learning. So now you don't have to do that compromise anymore.
We referenced the partnerships a moment ago. The two principal ones that I want to get into are the partnership with Hamamatsu, which was struck, and both of these were actually struck in the last 12 months. Hamamatsu and Teledyne Photometrics, just about a year old at this point. So it's been a very impactful year for Dotphoton. Prism Award finalist, Vision Startup, World Competition spot. How has the company managed to move from startup, which is something else you referenced a little bit earlier, to a company that's now sharing its message in a broad swath of different application areas?
It's actually, we see the pull from users. The way it works typically is that the end users say, well, I bought this great new camera, but I can't use it to its full potential because the images look amazing, but there's just too many of them and they're too large. So I need to compress them. So typically they then go to their camera manufacturer and they say, well, actually, do you have a solution to this? And at that point, the camera manufacturers come to us, and often we know them on the personal level because we maybe go to same conferences, and they ask, well, could we have an integration to guarantee that our systems work well together? And we have worked on that. So typically what that means is that, well, they send us their cameras so there's still some physics in our system. So they send us their cameras so that we can calibrate them in the lab. We verify that what happens in our lab is reproducible in their lab, so that we are aligned on the definitions and on the methodology. And then we exchange data in order to make the calibrations possible for the end user. So like they get the camera calibration and they get it gets embedded via our software in the compressed files, and then they can reuse it for other applications, not just for the compression.
I think I may have mentioned this too, the Jetross solution, which is in many ways the bread and butter of what Dotphoton is working on. Just to take a step back, you describe that for our listeners.
Yes. So the Jetross solution is, it's a compression for raw data. It has the upside that it achieves a compression ratio between 4 and 8. So in biology, you typically get 8 times compression ratio. In aerospace, because images are very detailed, we get a 4x compression ratio, and it's exclusively for raw images. So it relies on a mathematical model of the physical camera. So we need to get that model from the manufacturers, and then applying that model to our software uses that model in order to achieve this higher compression ratio. It's also very fast. It has a FPGA and software implementation. So typically you can keep up with the speeds of the fastest cameras. And that's also a particularity. It's very difficult to get software that is fast in both compression and decompression and in hardware and software. And also that has a good compression ratio and good quality. So what we strive to achieve is good performance in all of these aspects. From the end user, we try to make it really transparent. So the end user doesn't often know that anything is happening, apart from the fact that when he's sending images through the network, they are faster, especially for cloud applications. The compression is made completely transparent. So you get a raw file, which is a standard raw file in the format that you saved it in. And then when you send it through the network, we have a network proxy which can compress that and which can, on the fly, as you send it to the cloud, and save it in a compressed format in the cloud. And then when you go to look at it, it downloads the compressed file, and then the proxy so the proxy is a software that can be installed either on a real physical server, on a virtual machine, or also on the local desktop or laptop. It will transparently, kind of at the file system level, decompress the image so that you don't actually see any difference. Apart from the speed, we can open some files on the cloud faster than you would on your local PC very often. I mean, in Switzerland, we're lucky we've got gigabit connection to the cloud, but it is quite impressive working with cloud files as fast as you would locally.
Key to the Jetross solution and the core of Dotphoton's technology is the ability to combine distinct image types, for instance, lossy and lossless. The process of lossy image compression removes some amount of the data from the image file, which reduces the file size overall. A lossless compression avoids a degradation in image quality, removing non-essential data only. As it turns out, merging the two compression types opens doors to a world of useful tricks and applications. It's something that Dotphoton does well, and something that has helped the company to penetrate non-medical markets, including aerospace and manufacturing, where data also runs abundant.
Correct me if I'm wrong, but my understanding is that when it comes to image compression, the ability to combine a lossy format, which is very flexible, and a lossless format, which is kind of very reliable to use, that opens a lot of different possibilities once you have that accomplished. What are some of the applications outside of the life sciences now that the company is looking at?
Outside of life sciences, so we work with aerospace. So the director of our board used to be a director of the European Space Agency. So we have a natural tie with aerospace, and of course satellites. Often their ability to image is constrained by the download bandwidth. So that's a natural fit for us. We currently work with European Space Agency mainly, but if we expect that to grow soon. There's just a lot of certification and a lot of bureaucracy probably in getting systems ready to fly on satellites. The other interesting part is as well in automotive. So there's lots of data which is being generated by autonomous vehicles, whether they are cars or UAVs, and so we see a lot of growth in that area as well. But it is like we have customers on all sorts. Like we have a partnership with a local company who works in vertical farming. So they have a plant happiness index that is also a machine vision thing. And so there they have a cloud system. And so that's another application. Also in Switzerland, there's quite a bit of manufacturing. So you want to maybe do the analysis instead of locally. You want to do your analysis of manufacturing quality of the components on the cloud with some machine learning systems, and to transfer your images from the customer's devices all the way to do the analysis in the cloud. That's where we see some pull as well.
I don't mean to put a label here on what you and the company are doing. Image compression is at the core of it. I think that's probably fair to say. You've talked and you've presented many times on coming face to face with this data beast, right? There's so much data, and our ability to handle and use it in a constructive way is improving, but it is somewhat daunting, to use that word again. Do you have a sense of what technologies or industries or application areas might be featured in this next wave of data management innovation?
So we see, maybe because of the people who contact us. So we see growth in data everywhere, especially in image data, because it's so big, because it grows across so many different dimensions. So like suddenly you can get spectrally resolved data. Now in biology, it used to be that you had always a flat 2D image, which was a piece of dead tissue. And now life scientists say, well, it's called life science. You need to have live tissue. So that means it's videos which are 3D and sometimes spectrally resolved. So you do see a lot of growth there. we see growth everywhere. I think for us, the problem is really the opposite, is focusing on just a few sectors where we can make the workflow as easy as possible. But when you mention the data beast, it's true that it is a beast. Like once you have billions of files, it's very difficult. Just listing the files takes hours. Just moving the file, organizing the files, knowing who generated which files, how they were, what format they're in, and so on. It is very challenging. And so we started with just compression, but we see that the taming this beast is something which goes beyond that. It goes in like, how do you organize the data well? How do you make sure that it's fast to transfer? How do you make sure that you only transfer it when needed? How do you make sure that you've got all the right metadata? And so we are very much working in that direction, because the compression technology, in a way, it works. It went through a lot of certification, so it's now kind of very stable. And so we do have a fairly large engineering team, so we do keep ourselves busy. And the other aspect that we see as very useful is, and there's a lot of innovation in recent months even, is the generation of synthetic data. Because until now it was difficult and costly to do machine learning, especially because if you wanted to label data, you had to do it by hand. Whereas if you can now generate synthetic data, you don't need to do hand labeling anymore. You can, for example, in a demonstration we have done in aerospace to find cars from satellite images, from images from a fairly small satellite. And if you can't label the cars by eye because you can't see them by eye. But so we started off with some drone images where you could even automatically label the cars. And then through an end-to-end model, we generated some images which emulate exactly how they would be had they been taken by a satellite. And there you couldn't see the cars, but the machine learning, because we still had labels for the cars, and the machine learning could learn with a fairly good accuracy to identify those cars. And so the results you can have quite impressive. And I think with machine learning, we're at the stage where in some cases you can get performance which is bigger than what you can do with your own eyes, with human eyes. And so this is where I think in the next few years, there will be some probably revolution in that aspect, is what can you do with machine learning that you can't do by hand, with your own eyes.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.